Okay, now I'm showing my screen. Okay, so last time I stopped somewhere here, so I just went a couple of slides back. So this is a system of partial differential equations that describes stellar structure and its evolution. As you can see, yeah, because usually we compute stellar structure and evolution in only one dimension, therefore there is only one spatial independent variable radius. All partial derivatives are with respect radius, and I thought that I raise a question. So you may wonder from these equations what actually causes the evolution of the star, what causes the changes of stellar structure, because there is no explicitly time seen in these equations. Okay, so the answer to this question is, of course, the evolution of the star is caused by the change of its chemical composition, or in other words, by the change of mean molecular weight, because pressure, energy sources, and stellar opacities, all these physics variables like kappa, opacity, pressure, internal energy, as well as energy generation rate, they are all functions of, as you can see, of the chemical composition. Okay, for instance, X, Y, Z, hydrogen mass fraction, helium mass fraction, and mass fraction of heavy elements, or pressure, for instance, ideal gas pressure is a function of the mean molecular weight. So therefore, it is the change of the chemical composition caused by nuclear reactions, thermonuclear reactions, because of very high temperature that lead cause the change of stellar structure and the evolution of the star. So therefore, these four equations of stellar structure and evolution have to be supplemented with equations of the kinetics of stellar nucleosynthesis. One of them is shown here, just an arbitrary equation. And the equations of the kinetics of stellar nucleosynthesis, they actually describe how the chemical composition of the star changes inside it. Okay, we discussed this last time as well, so I'm not going to discuss the slides again, just this important note that I wanted to add. So now, this question of stellar nucleosynthesis are either the first one in terms of number fraction and the number of isotopes of type K in one, say, cubic centimeter, or equation written for the molar abundance Y. Okay, you can have more detailed look at this slide later. Okay, in either case, this is just an exemplary equation. It assumes that there is a fusion between isotopes I and G, and the isotope of type K can also experience decay with a characteristic exponential lifetime tau. So this is just some template equation, not a specific one, but it shows that in principle we can write equations like this with much a larger number of terms on the right hand side for each isotope. Okay, and these equations will, when we solve them, then will tell us how abundances, number densities, mass fractions of all isotopes that we want to study change with time, and these changes actually cause the evolution of the star. Okay, so schematically, as you know, probably all nuclear reactions can be illustrated on a chart of nuclides, like this one. So usually on the charts of nuclides, the horizontal axis going from left to right shows the number of neutrons, and the vertical axis going from bottom to upwards shows the number of protons. So a diagonal line here, which shown with blue, dark blue color, is called the value of stability, as you probably should know already because you're a nuclear physicist. And it shows the value of stability shows stable isotopes. And any nuclear reactions on this chart of nucleids can be shown with an arrow. For instance, if we add to any of these isotopes 1 neutron, for instance, if we take neon-22 and that 1 neutron, this means we go to the right, we produce neon-23, okay? But if we neon-22 captures proton, we go upwards, we get sodium-23 and so on. Of course, you should be familiar with charts like this, okay? So I'm not going to stop here any longer. Of course, this is just for completeness of my lecture, but I expect that, of course, you should know this too. So this curve here shows the so-called the nuclear binding energy per nucleon. And it's well known that this curve has a maximum in the region of the so-called iron peak elements. It's called therefore iron peak because it has here a peak, but it's not a sharp peak. It's relatively smooth here maximum. So it's this binding energy per nucleon, it shows actually that nuclei or isotopes to the left from iron peak, okay, they can be produced with a release of energy, because when we go from lighter isotopes to heavy isotopes, when we fuse heavy isotopes from lighter, this releases nuclear energy, and binding energy becomes higher because some energy was released. On the other hand, when we go to the right from the iron peak nuclei, the binding energy decreases, which means that these heavy elements cannot be produced in fusion reactions because they would need some energy. And as you know, as I will show you soon, these elements heavier than iron, they are produced not in charged fusion reactions, but instead in reactions of neutron capture. For neutrons, there is no Coulomb barrier, so it's easier, much easier to synthesize these elements as a result of neutron capture. So you should be familiar with nuclear binding energy curve, of course. So now I'm just going through main chains of nuclear reactions that occur in stars. So when a star evolves, remember, star begins its evolution from the so-called main sequence, where it burns, transforms hydrogen into helium in its core. And hydrogen burning in stars occurs in two major chains. The first one is called proton-proton chains. Proton-proton chains. There are several proton-proton or PP chains, as you can see in this diagram. Yeah, I'm sure you're probably also familiar with these chains. And these chains work predominantly. So in just a second. Okay, these chains work in solar type stars, for instance, in the sun. Yeah, so they work at lower temperature. At higher temperatures, yeah. So and this figure shows solar neutrino spectrum for PP chains measured experimentally, which actually confirms that at the center of the sun, our closest star, we do have reactions of PP chains going on. Okay, all these neutrinos that are formed in different PP chains, you can see. For instance, here neutrino is formed, here neutrino is formed. This is called a boron neutrino, one of the first neutrinos which was sought for this neutrino. By now, all these neutrinos produced at the center of the sun were already experimentally detected. Okay, and there were a few Nobel Prizes actually given for neutrino detection in the sun, as you know, and this text here actually reminds us that the total neutrino flux from the sun measured at Earth is approximately 10 to the 11 neutrinos going through one squared centimeter per second. Guys, could you please mute your mic? Yeah, thank you. So approximately 10 to the 11 neutrinos crossing each square centimeter per second. If I, for instance, direct my palm towards the sun, wherever the sun is now, this means that through my palm, through each square centimeter of my palm, there are approximately 10 to the 11 neutrinos crossing it per second that were formed at the center of the sun about 8 minutes ago, because it takes about 8 minutes for neutrino to reach from the sun to Earth. Okay, the second major chain of hydrogen burning in stars is, as you know, CNO cycles. They're called in plural cycles because there are several of them. This one, the left one, is called sometimes just CN cycle because it mostly involves carbon and nitrogen. Oxygen 15 is radioactive, it decays to nitrogen 15. This is CN cycle or cycle 1. There is cycle 2, cycle 3, and cycle 4. So CNO cycles of hydrogen burning work in more massive main-sequence stars, more massive than the solar mass, around approximately 1.3, 1.4 solar masses on the main-sequence. There is a switch from PP chains to CNO cycles, as next slide will show you. So more massive than the sun stars on the main sequence transform hydrogen into helium in CNO cycles. Okay. Additionally, we should also consider the so-called neon sodium and magnesium aluminum cycles, because here we have higher electric charges of nuclei. Therefore, Coulomb barrier is higher, and we need a higher temperature to penetrate the Coulomb barrier. So neon sodium and magnesium aluminum cycles, they don't work in full in main sequence stars. Only a few reactions from these cycles may occur in massive intermediate mass and massive main sequence stars. In particular, reaction neon 22 p gamma sodium 23. It occurs in a convective course on massive and intermediate mass main sequence stars during hydrogen burning, just because this reaction has a low energy resonance. So therefore, it goes relatively fast, even on the main sequence, but not in the sun, but in more massive main sequence stars. Okay, so the temperature, characteristic temperature range are shown here. T sub 9 means temperature measured in billions of Kelvin, so 10 to the 9 Kelvin. So therefore, this means neon sodium cycle works in full from about 40 million Kelvin to about 400 million Kelvin, and similar for magnesium aluminum cycles. Okay. As I said, as you of course also know, there are two effects that actually hinder thermonuclear reactions of going on inside stars, not only inside the stars, but anywhere. The first effect is Coulomb barrier that I already mentioned. Okay, this Coulomb barrier, which hinders thermonuclear reactions from going on, because charged particles have to overcome this Coulomb barrier. The second effect that hinders nuclear reactions is the angular momentum conservation, okay? Because we would like to have a direct collision, which means angular momentum equals 0, because if angular momentum is not 0, and conservation of angular momentum would require that momentum is conserved. So this is the second effect that hinders nuclear reactions to go inside the stars. And as you already, of course, know, that Coulomb barrier, fortunately, can be penetrated through the effect called quantum tunneling, right? So, but instead of going over the Coulomb barrier, the particle can, of course, as you know, tunnel through the Coulomb barrier. You've studied this, of course, as a nuclear physicist. So I'm not going to stop on this. But this is an interesting thing. Probably, maybe you don't know this, but as a stellar astrophysicist, I know this, and let me just explain this for you. If we calculate the efficiency of quantum tunneling through Coulomb barrier, okay, this effect of quantum tunneling is described here by this exponential curve on the right here. It says tunneling through Coulomb barrier is proportional to exponent of particle energy E in the denominator. Okay, the higher the energy, the easier, of course, for a particle to cross Coulomb barrier via quantum tunneling. Okay, but this curve here on the left, this curve, it shows actually a distribution of particles inside the star according to Maxwell-Boltzmann distribution of the energies. Okay, and as you can see, the efficiency of quantum tunneling becomes high enough only in the tail of Maxwell distribution, only in the tail. Okay, so which means, and the product of these two curves, the left one and the right one, is shown here by this peak here at the center, which is called, as you know, a gamma peak. Okay, so it shows the energy, which is called gamma energy, at which these two distributions, Maxwell-Boltzmann and the efficiency of tunneling, they give you the maximum probability. And as you can see, gamma peak energy, its energy is located in the tail, in the outer tail of Maxwell-Boltzmann distribution, which means that in stars, we have thermonuclear reactions going only for particles that are at the very outer tail of their Maxwell-Boltzmann distribution in energy. Okay, fortunate for thermonuclear reaction situation occurs when the gamma peak energy coincides with the energy resonance in a given nuclear reaction. So this is shown here. For instance, if we take one of the nuclear reactions from pp chains, beryllium-7 p gamma boron 8. So this is its cross section, data points, experimental cross sections. As you can see, this reaction has here a very sharp peak at this energy, and this peak corresponds to resonance in this cross section. And if, for instance, temperature in the star is such that gamma peak energy is close to this resonance energy, then this reaction will be going these thermodynamic conditions very rapidly. So therefore, the presence of resonances in cross sections of some nuclear reactions, for instance, I mentioned neon 22p gamma, makes some of these reactions going very efficiently at some temperatures, even at low temperatures, if we have low, so-called low energy resonance, right? Okay, so this plot that I promised you, it shows at which temperature there is a switch from pp chains to CNO cycle. So horizontal axis here shows hydrogen core temperature in the main sequence stars, going, say, from 5 million to 30 million. Okay, and the vertical axis shows the relative energy generation rate in pp chains, blue line, and in CNO cycle, red line. And you can see there is a crossing of these two lines, which occurs at approximately temperature around, I would say, 17 million Kelvin. In the sun, the central temperature in the sun is around 15 million Kelvin. So therefore, in the sun, hydrogen burning occurs via pp chains predominantly. But the temperature in the sun is close to this crossing temperature. Therefore, there is non-negligible hydrogen burning in the sun also occurring in the CNO cycles. And even neutrinos from CNO cycle were also detected from the sun. Okay, so the mass of a main sequence star increases from left to the right. So the higher mass stars on the main sequence have higher, of course, central temperature. So therefore, you can see that low mass stars on the main sequence stars with masses slightly below 1.3 solar masses, they burn hydrogen in PP chains, while more massive stars burn hydrogen in CNO cycles. Okay, and by the way, because the sensitivity to temperature for CNO cycle, because of higher higher electric charges of CNO nuclei compared to protons and helium, this temperature sensitivity is much stronger for CNO cycle. Energy generation rate is proportional to temperature to the power 17 versus temperature to the power 4 for PP chains. This explains why stars more massive than the sun have convective cores in the center, while sun and solar type stars have radiative cores. Because the energy production, the CNO cycle, is so temperature efficient, radiative heat loss, which is proportional according to Stefan-Boltzmann law to temperature to the power 4, cannot transport heat efficiently enough. Okay, so therefore convection sets in. So therefore this plot also explains why more massive main sequence stars have convective cores while less massive stars have radiative cores. Okay. When the star leaves main sequence, when hydrogen is exhausted in the center, it has now helium core. Helium core grows in mass because after that hydrogen is still burning in the so-called hydrogen burning shell atop of the helium core. And when it burns, it adds more and more helium to the core. The helium core mass grows. And eventually, helium core mass becomes so large that its compression will lead to an increase of temperature up to about 100 million Kelvin. And then the next major phase of nuclear burning will start in the helium core stars, which is called the triple alpha process. When we have fusion of 3 alpha particles that form carbon-12 nuclei. Okay, of course you have heard about this, but for completeness, my slides include this the very important reaction, the triple alpha process as well. Okay, so now I told you, I showed you the equations, 4 equations of stellar structure and evolution, right? Partial differential equations, plus a number of equations of stellar nucleosynthesis. Okay, the number of equations of stellar nucleosynthesis can be any, depends on how many isotopes you want to include in your study. You have to always include at least those isotopes whose nuclear burning produces quite a lot of energy. Otherwise, you will not construct a right model of the star, because all important energy producing nuclear reactions have to be included, right? And the next question is, how can we solve those equations? Those equations are highly nonlinear, so therefore they cannot be solved analytically. Therefore, we use numerical method to solve those equations. And fortunately, now we have a publicly available code, which is called MESA, M-E-S-A. Yeah, you've heard about this code, and I'm using this code, and thousands of researchers around the world use this code. So I'm going to advertise this code because I think this is this is like Hubble Space Telescope for theoretical stellar astrophysics. Okay, and this slide here, it's linked to animation from actually MESA website, which shows animation of the evolution of a solar mass star, actually the evolution of the sun. I'm just going to show you, I'm not going to run it fully, it takes about 5 minutes. I will just show you the main plots and the main evolutionary phases here, right? Okay, so let me, okay, I'm going to pause it. Like here, okay. Oh, just a second. I'm going to pause it here. So let me just show you You can add here different plots. So this is just some standard set of plots. I'm not going to go in much details. Let me just show you the main subplots. So this one on the top left, it shows theoretical Hertzsprung-Russell diagram, a fragment of theoretical Hertzsprung-Russell diagram. I mentioned it last time. So this means we plot the decimal logarithm of effective temperature at the surface of the star as a function of decimal logarithm of luminosity of the star, right? So this is like a phase diagram in physics to study the evolution of stars in these two surface variables, surface temperature and luminosity. And this blue line shows the so-called evolutionary track. It shows how the position of the star on Hertzsprung-Russell diagram changes as it evolves, okay? So now this bottom left plot is not that interesting. It just shows how, it's probably interesting for nuclear physics, of course, because it shows how central density versus central temperature changes inside the star. You can see temperature is now above 10 million already at this position of the star. Density at the center is now 1,000 gram per cubic centimeter, because this solar mass star has already left the main sequence. So it's already left the main sequence. How we know this, that it's left the main sequence? Because this plot here in the middle in this panel, it shows, as you can see, decimal logarithm of mass fractions x sub I of different isotopes. And if we have a look at hydrogen is shown here by blue. You can see hydrogen goes to 0 at the very center, which means hydrogen is exhausted in the center. We have instead helium, yellow, here at the center. So that's it. Let me just run this a little bit to show you, to demonstrate how we can observe the calculations done with the mesostellar evolution code as it proceeds, okay? I'm not going to go into details because it's a pretty complicated movie. I'm going to move just further. So MESA code captures actually allows to simulate even helium core flash inside low mass stars, which was impossible to do with previous stellar evolutionary codes. It was a very difficult task to do. And now we are at the moment when the star experiences a series of helium core shell flashes before helium burning will be settled inside the star. Okay, let me move further on. Okay, so now the star has already exhausted helium in its core, and it's on the asymptotic giant branch, so-called. I'm going to move further. Now the star experiences helium shell flashes on the asymptotic giant branch. Unfortunately, I don't have enough time to explain all details, but you can have a look at this movie later in the slides. Okay, let's go further. When the star is on the asymptotic giant branch experiencing helium shell flashes, it also loses mass. Eventually, it will lose mass in the so-called high mass loss. And when it loses mass, the lost mass in this case is observed as planetary nebula. You've heard about planetary nebula. And after the star has lost almost its entire hydrogen envelope, it leaves the asymptotic giant branch here. It moves horizontally to the left to the white dwarf symmetry. So it will end its life. The solar mass star, the sun, will end its life as a carbon-oxygen white dwarf. So this is the last hydrogen shell flash here. Okay, and then it moves to the white dwarf symmetry at very low luminosities. So now just a second. Yeah, now it moves here down. It cools down. This is carbon-oxygen white dwarf, the remnant of the evolution of the sun. And you can see it moves to very low luminosities on a very long time scale, several billion years here, okay? Okay. So now let me go further. Okay, so this slide summarizes the main evolutionary phases of low and intermediate mass stars. So one solar mass star, you just saw it's a MESA movie, right? This one. So I'm not going to repeat it. We start with main sequence. Then after the main sequence, we have the so-called subgiant branch, then red giant branch, almost vertical. The helium core flash occurs at the tip of the red giant branch here, and a series of helium shell flashes, helium core burning is then established at the center, and the star from the tip of the red giant branch then finds itself on the 0H horizontal branch here, okay, the low mass star, one solar mass star. And on the horizontal branch, the star burns helium in its central convective core. After helium is exhausted, so on the main sequence, hydrogen burning, on the horizontal branch, helium core burning. After helium is exhausted on the horizontal branch, the star moves to the asymptotic giant branch here, and then it loses mass in the form of planetary nebula at the tip of the giant branch here, after experiencing a number of helium shell flashes and moving up and down here, as you can see in the previous movie. And then when the planetary nebula is lost, and we have a naked, almost naked carbon-oxygen core or carbon-oxygen white dwarf, the star moves almost horizontally to the left. This loop corresponds to the last hydrogen or helium burning shell here, the last helium burning shell. And interestingly, there are stars that are captured on this evolutionary phase. For instance, Sakurai's object or FG Sagittarius star is captured exactly during this evolutionary phase. After this last helium shell flash, the star finally moves to the white dwarf symmetry, white dwarf cooling sequence, this one. A more massive star, for instance, 5 solar mass star, it also begins its evolution on the main sequence, then it crosses this region which is called Hirschsprung gap, because the stars with intermediate masses cross this region very quickly. So therefore, we cannot expect to see many stars on the sky during this short time. Then it has red giant branch evolution, blue loop, where we can find classical Cepheids pulsating stars, which were used to determine distances even to the nearest galaxies. Then asymptotic giant branch phase, and after losing its mass in the form of planetary nebula, we have more massive than for one solar mass star, white dwarf, which can be instead of carbon-oxygen white dwarf, it can be now oxygen-neon white dwarf, for instance. Okay, so this is the evolution of HGB stars of masses of 1 solar mass and 5 solar mass star. Okay, so this plot summarizes what I've just told you, the major evolutionary phases of low intermediate mass stars. The important things here to remember that low mass stars, this is mass is shown here, 1 solar mass up to approximately 4 solar mass, they're called low mass stars. They experience, the lowest masses experience helium core flash, higher masses don't experience helium core flash. But these low mass stars and the evolution as carbon-oxygen white dwarfs up to the 8 solar mass, okay? And more massive stars leave as remnants oxygen-neon magnesium white dwarfs here. I'm not going to talk about massive stars so far right now. Low mass stars during the asymptotic giant branch evolution, they are important because they are known to be a source of S-pros nuclear synthesis, of S-pros nuclei, of S-pros. So S-process nuclear synthesis occurs, it can occur also in massive stars, but the main S process occurs in low mass HGB stars. I will show you later. Okay, here. So this is how this S process nuclear synthesis. S process nuclear synthesis, S stands for slow. This is a slow process of neutron capture. Okay, how it occurs, this S process in low mass asymptotic giant branch stars. Okay, so these stars have convective envelope, which is shown here with this green region. Okay, and they have helium shell, which experiences recurrent flashes. So after the flash, and green region here shows convection. So this this green patch this is pulse-driven convective zone. This is a convective shell or convective zone in which convection is driven by helium flash. Okay, this is the second flash or the third flash, whatever. HGB star, asymptotic Chandra star can experience several helium shell flashes. Immediately after helium shell flash, the bottom of convective envelope penetrates here into the region previously occupied by helium shell here, and it injects protons here. It injects protons here. Okay, injection of protons can occur through, for instance, some mixing by internal gravity waves or by some other mixing processes. And later, when the bottom of convective envelope recedes, and there are protons in this carbon 12 rich region injected here by some mixing process, these protons are captured by carbon 12, which produces carbon 13. And carbon 13 captures alpha particle, and this reaction releases neutrons. And therefore, it is believed now that S process in low mass HGB stars occurs in this region, which is not convective, in this region. Okay, and finally, this diagram summarizes shows actually paths of both slow S and rapid R neutron capture processes in stars on the chart, on the schematic chart of nuclides. So S process, slow process of neutron capture nuclear synthesis, usually starts with iron, and it goes to the right because we have neutron capture, which moves us to the right. And it moves to the right until the first unstable isotope is met. As soon as the first unstable isotope is met, it decays into isotope with a number of protons larger by 1 here. Okay, then this isotope captures neutron. As soon as it reaches the first unstable isotope, it decays, and so on and so on. So this is this black line shows the path of S process path, slow process of neutron capture. There is also rapid process of neutron capture, which is called R process. So S process and R process differ by the neutron density, the number of neutrons in cubic centimeter. For S process, the number density of neutrons is between 10 to the 7, 10 to the 10, 10 to the 11 neutrons per cubic centimeter. And because the number of neutrons is small, therefore, neutron capture process is cut at the first unstable nuclei. R process occurs in a stellar environment where there is much larger number fraction of neutrons, above 10 to the 20 neutrons per cubic centimeter. This can occur, for instance, during neutron star merger or in jets of co-collapse supernova, where there is a lot of neutrons. And in this case, because of a large number of neutrons, neutron capture process continues even, it includes even unstable nuclei, because the rate of subsequent neutron capture is much faster than the rate of beta minus decay. Okay, so therefore R process reaches neutron drip line here, beyond which neutrons are not neutrons are just cannot be bound by nuclei, and only then at the boundary of neutron drip region we have decay. But when our process stops, of course, all these unstable nuclei then decay along isobar lines towards the value of stability, okay? And there is also, of course, new P or P process, which is responsible for the production of proton-rich nuclei. We will talk about S process, R process, and intermediate neutron capture process, I process, which goes in between S process and R process here in between later, as well as about P processes, okay? This slide ends my slides that I call Introduction to Stellar Astrophysics. And here, then slide, there is one exercise for you. You may do this exercise or may not, it's up to you, but you can try to do this exercise, okay? So now, before I go to next topic, let me just ask you if you have any questions, guys. You have to please unmute yourself. Yeah.
I have a few questions. The first one is the Coulomb barrier. You mentioned that the tunneling probability becomes small, but you said it's the reaction cannot really happen because of the angular momentum. I didn't really understand why that would be the case.
Oh, no, I mean, this is there are two effects that make probability or rate of nuclear reactions slower than it could be otherwise, right? The first one is the presence of Coulomb barrier. For instance, when we consider neutron capture reactions for in S, I, or R process, for neutrons there is no Coulomb barrier, so therefore there is no this effect. But angular momentum conservation, for instance, if you have two particles which don't approach, they don't approach each other head on, but they have a relative angular momentum like this, L equal 1 or L equal 2, right? Then compound nucleus, if they form a compound nucleus, we still have to, this reaction still has to obey the angular momentum conservation, okay?
Wouldn't that just leave the product of the reaction in the excited state?
Yeah, if there is the corresponding excited states with the corresponding momentum, right? Yeah, but also I have to tell, I have to tell, guys, could you please mute those of you who doesn't ask the questions, because yeah, otherwise we have echo if you didn't yet so far. Look, I think you should know answer to this question better than me, right? Because I'm stellar astrophysicist, right? Okay. So maybe this is I who has to ask you the question like this. Okay, I just read about this in the literature. Okay, but I understand this how I understand this. Okay, this is my understanding of it. But probably you should know this better because you're a nuclear physicist, right? I don't know everything about, of course, nuclear reactions. We are going to collaborate, and this is a question for you. Okay, thank you. Other questions, guys?
Also, yeah, I had another question. The AGB, you say AGB star loses its mass by forming the planetary nebula, and how does that form planetary nebula and lose?
Yeah, this is a good question. Unfortunately, there are many questions in stellar astrophysics that we don't right answers yet, okay? And this is one of such questions. Now I actually recall how this event is called. It slipped out of mind. It's called superwind phase. So we believe that at the end of the asymptotic giant branch evolution of low intermediate mass stars, the star experiences the so-called superwind mass loss, superwind, okay? And this leads to the formation of planetary nebula, which are ubiquitously observed, right? So the question is, what causes the superwind phase? There is no definitive answer yet. The possibilities how to answer the question is we know that during the asymptotic branch phase, during this intermittent during this recurrent helium shell flashes, the star experiences pulsations. It's actually, you can see even in the animation that I showed you, during it moves up and down, and this can cause shock waves in its envelope, these pulsations, okay? And shock waves can lead to enhanced mass loss. Also, because these stars are very cold and they have very large radii, at the outskirts of the envelopes, temperature is so low that we expect, we know that there is formation of dust, molecules and dust. And then radiation pressure acting on dust and molecules, it can also help to remove the envelope very quickly at the end of this evolutionary phase. But there is no definitive answer to this question yet, okay? Yeah, thank you for the question.
Thank you.
Yeah, more questions, guys? Okay, if you don't have any questions yet, let me just remind you that you can download the slides, okay? And if you have any questions later, please ask me either via my email or via Mattermost CaNPAN channel, okay? Don't hesitate to ask me questions. So now I'm going to go to the second topic, to the second set of slides. This is about nova stars, nova explosions, nova evolution, okay? Because after that, I will show you how you can actually already run some simple nuclear synthesis simulations for novae, okay? So therefore, I will precede this explanation how you can simulate nova explosions with a few slides, okay? So let me switch to the second set of slides. Let me just go here. Nova, okay. So now our CaNPAN projects will, as you know, will include studies of nuclear synthesis at different stellar sites, okay. I begin with nova. Okay, and today I'm going to give you to present for you several slides about novae, and also to explain you how you can run some easy nova nuclear synthesis simulations. Okay, so let me start. This is CAN project's nova introduction. There are just a few slides. Okay, just a second. Here. Okay, so these are general comments that are applicable to all our CaNPAN projects. Let me just read it. So first of all, the main, and also these slides are also in the same repository. You just have to find it. So you saw the directory Stellar Astrophysics, and you also saw the directory NOVA. When you go to directory NOVA, there will be directory notebooks. Go to directory nova/notebooks, and you will find these slides about novae. So these are general comments on all CaNPAN projects. The main goal of the CAN projects is to provide Canadian nuclear physicists and stellar astrophysicists with computational tools that will help us to collaborate on identifying and solving problems of mutual interest. Okay, most of these problems are about nuclear reactions going in stars and leading to the production of chemical elements and their isotopes in the universe. To quickly reach the goal for each project, I will go through the following steps. I will first briefly describe a stellar site where nuclear reactions you want to study are likely to play an important role. Then I will demonstrate you how the evolution of thermodynamic and mixing properties of this site can be simulated with a stellar evolution called MESA. And I will also explain how to use results of MESA simulation for one and multi-zone post-processing nuclear synthesis computations with the new grid codes PPN and MPPNP. And finally, I will show you how to set up and run the new grid post-processing nuclear synthesis computations for Monte Carlo reaction rate sensitivity and uncertainty studies. So this is applied to all our CaNPAN projects. After now, we will have X-ray burst and R process, P process nucleosynthesis during X-ray burst nova on neutron stars, on the surface neutron stars, then I process, P process, and so on. Okay. Now we talk about nova explosion simulations. Okay, just a second. Okay, so this figure explains environment, a stellar environment in which we know nova explosions are observed, occur. Okay, so nova explosions occur in closed binary systems on white dwarfs accreting hydrogen-rich material from their main sequence, subgiant or red giant branch companions. Okay, so in many cases, we have, instead of the evolution of a single star, we have the evolution of two stars in a binary system, okay? Because at solar metallicity, at least 50% of stars are members of binaries. At low metallicity, even a higher fraction of stars are in binaries and triple systems, okay? So if a binary system is initially already close enough, then we have a situation like this that occurs during nova explosion, when we have here on the right side, we have a white dwarf, okay? And on the left side, we have a main sequence companion of the white dwarf, okay? And this star, because its radius increases during its main sequence and subgiant branch and red giant branch evolution, the companion, white dwarf star companion, main sequence star, can eventually fill its Roche lobe. Roche lobe is the region inside which gravitational attraction is dominated by this star. But when the star fills its Roche lobe, material from the star can freely cross into a Roche lobe of its companion, in this case, white dwarf, through the so-called inner Lagrangian point. Okay, this material we say the main sequence companion donates its material to white dwarf companion. The donated material forms an accretion disk, and eventually this material from the disk will be accreted by the white dwarf. So this can, of course, happen only in a closed binary system, and observations confirm that novae occur in closed binary systems. So the nova explosion will occur when the accreted material will reach a critical mass on the white dwarf. Okay. So you can have a look at this slide yourself. It just shows how in the Python notebook you can import relevant astronomical and physical constants. I'm not going to comment on this slide. We will have a look at it later. Similarly, this slide, it shows how you can calculate Roche lobe radius for white dwarf and for companion. Here, for instance, you can provide your own parameters. Here I choose a mass of the white dwarf and solar mass is one solar mass. This is, for instance, for carbon oxygen white dwarf. Mass of the companion in solar mass is 1.5 solar mass star. Orbital period of white dwarf around its main sequence companion in hours, 4 hours. This is a typical orbital period for white dwarfs in nova systems. They're called also cataclysmic binaries nova systems. And there is here a link, a reference from the reference to a paper which provides a table of orbital periods for nova systems. Then I do some calculations, the mass ratio of white dwarf to its companion, and I use some equations with provided references, unless this is a well-known law like Kepler's law, and I calculate a Roche lobe radius of white dwarf and its companion. So if we execute this cell, we will get these results. First, the semi-major axis of the binary system, A, this is separation of two stars in the binary system, in solar radius 1.73, Roche lobe radius of the companion star 0.717 in solar radius, and Rho slope of white dwarf is 0.596. You can just play with this cell later. So now about some information about nova observables, actual and possible observables of nova explosion nucleosynthesis. I mean, ideally, we need some observables to compare with predictions of our models, right, of our calculations, of our simulations. So for novae, observables are the following. So suddenly a new nova means new star, appears in the sky, and which is caused by an increase of white dwarf luminosity from its ordinary luminosity, which is 10 to the minus second solar luminosities. Luminosity increases to 10,000 solar luminosities. And we have 3 to 5 novae observed per year, although statistics shows that there should be 30 to 50 novae in our galaxy exploding every year. Okay, they are not observed because probably of dust, because they belong to the population 1, to the disk of our galaxy, which is very dusty, so therefore probably we just don't see them. Instead of 30 to 50, we see per year 3 to 5 novae, but quite a large number, 3 to 5 novae per year are observed. The next observable for novae are optical, ultraviolet, and X-ray light curves from a deepening nova photosphere. After nova explosion, it ejects its accreted material, its atmosphere, its envelope. And when this envelope is expanding, it becomes more and more transparent, which means that the photosphere of the nova, and photosphere is the layer which is transparent to radiation in continuum. And because of expansion of the envelope, the photosphere is deepening. So the photosphere, the radius of the photosphere recedes, okay? And therefore we gradually, first we can see optical radiation, then ultraviolet, and finally X-ray, because we see hotter and hotter layers of the envelope. Eventually X-ray, we see the surface of the white dwarf, where temperature is around 1 million Kelvin, so therefore we have we see X-ray radiation. Okay, then we can use as observables for novae elemental abundances in nova ejecta, directly determined spectroscopically using the optical, ultraviolet, and infrared emission line spectra. For instance, there is a link here, a reference to table 2 from this paper, where mass fractions of hydrogen, helium, and CNO elements were measured in a number of novae. You can have a look at this link. Next observable for novae, gamma lines. In principle, some of these observables have already been observed. Some of them are not, have not been observed yet. And I say if it was observed or not. Gamma lines are expected to be seen from novae from electron-positron annihilation at 511 keV, kilo electron volt, with adjacent continuum at lower energies, okay, cut at 20-30 kilo electron volt. Also, we expect, I mean, we ideally would like to see gamma lines from novae at this wave, at these energies, 478 keV, 1275 keV, and 1.809 mega electron volt from decaying beryllium-7. Its lifetime is 77 days. But it depends on temperature and density, respectively from sodium-22 and from aluminum-26. Unfortunately, these gamma lines have not been observed yet, okay, in spite of all attempts to observe them with gamma ray space telescopes. Finally, observables for novae can be peculiar abundance ratios for CNO intermediate mass isotopes, producing non-equilibrium CNO, neon, sodium, and magnesium aluminum cycles and beyond, up to atomic mass 40. And these ratios are observed, they are measured in meteorite dust, we believe, okay? So for each stellar nuclear synthesis sites, as I said, let me just emphasize that we need, in principle, to find, to think of some observables, because we need to compare our predictions of theory, right, with some observations. Otherwise, it doesn't make sense, right? Okay. Okay. So this figure shows a photo of real nova explosion. This is Hubble Space Telescope images of nova Cygni 1992, taken 7 months apart. Of course, earlier on the left side and later on the right side. You can see that ejected nova envelope increases in radius because it expands, and this is just a real observation, photometric, real photometric observations of a nova explosion. Okay, so in this project, in this nova project, we will focus on hydrogen burning nuclear synthesis in one dimensional, as I said before, hydrostatic nova models, rather than on nova photometry or spectroscopy at different color bands or wavelengths. Because you are nuclear physics experimentalists and I'm stellar nuclear astrophysicist, we are not going to discuss observations, right? We don't have observers among us. So therefore, we will do stellar nuclear astrophysics modeling with your help, with your collaboration, and compare with available observational data, if there are any. So the hydrogen-rich material accreted by the white dwarf, carbon-oxygen or oxygen-neon white dwarf. So correspondingly, there are carbon-oxygen novae and oxygen-neon novae, okay? So the hydrogen-rich material accreted by the white dwarf in a closed binary system is being, as I said before, compressed by the force of gravity. And as a result of this compression, it's getting heated up until hydrogen is ignited, leading to a thermonuclear explosion. A large amount of heat released by this runaway hydrogen burning at the base of the accreted envelope triggers convection in the envelope and causes its expansion. It is interesting that a similar sequence of events, okay, this is just an interesting coincidence. A similar sequence of events, namely air intake, its compression, fuel injection, and combustion, finally followed by exhaust of burning products, exactly like in novae, takes place in a 4-stroke diesel engine. I will show you animation next. The similarity between the nova and diesel engine duty cycles is enhanced by the fact that a successful nova explosion also needs an injection mixing of carbon and oxygen or oxygen-neon-rich material from an underlying carbon-oxygen or oxygen-neon white dwarf that serves as catalyst for hydrogen burning. Now, this animation shows main stages of mechanical analog of novae is a 4-stroke diesel engine. So we have, as you can see, we have air intake, which corresponds to accretion of hydrogen-rich material by carbon-oxygen white dwarf. Then we have compression, then we have ignition, and we have exhaust. So therefore, I think this is a just funny analogy. Okay, just for fun. Okay. So now this is already familiar for you animation from MESA simulation. But in this case, it's not just evolution of one solar mass star. Instead, this is evolution of a nova-like explosion. Let me start it here. Okay. So let me just close this. Okay. So what is shown here, again, this is Hertzsprung-Russell diagram, luminosity, effective temperature. And what's shown here, mass fractions of various isotopes, in this case, CNO, neon sodium, and so on and so on. And what is shown here is the yellow curve temperature, and blue curve here, nuclear energy generation rate here, okay? And at the bottom panel, what's shown is the temperature gradients, nablas, okay? In the convective region, radiative temperature gradient, the brown line should exceed a diabatic one, the white one. And you can see as a result of hydrogen accretion, we have an increase of temperature. Yellow line goes to almost 100 million so far, okay? And we have hydrogen ignition in the C12P gamma reaction. This is the first reaction of CN branch. As a result, we have formation here of convective shell, which will become convective envelope later. And as a result, you can see the star on the Hershberg-Russell diagram will make a loop. So let me just turn this on. You can have a look at this movie later because we don't have. Yeah, you can see the star makes loop. So it ejected in its envelope. Now it begins to accrete hydrogen-rich material again. Again, explosion. It makes loop again. Okay. And so on. Okay, so it continues making explosions. Okay. So I call this a nova-like explosion. What's the difference compared to real nova explosion? The difference is that here you can see on mass fraction plot, these yellow curves show helium abundance, helium. And you can see that at the bottom of hydrogen-rich accreted envelope, the blue line, below this envelope, there is quite a thick layer of helium. This is called a helium buffer layer. It's left at the end of asymptotic giant branch evolution. Okay, it's always left. And before this helium-rich buffer layer, before it's erased, we will not have the true carbon-oxygen nova explosions. But the very fact that we do see carbon-oxygen nova explosions means that this helium-rich buffer layer is erased eventually, probably by mixing and by explosions. So at the very beginning of its evolution, nova should first erase helium buffer layer. Unfortunately, there is not much discussion in the literature of this thing, but I just pay your attention to this fact because this is an important thing. Okay, okay, just a second. Let me go further. Okay, so now summary: the strength of a nova explosion, which can be measured, for instance, by the maximum temperature of hydrogen burning during the nova explosion, and the envelope expansion speed. So the strength of nova explosion can be amplified, strengthened with an increase of the white dwarf mass. Of course, white dwarf mass cannot exceed the Chandrasekhar mass limit, approximately 1.44 solar mass. When it reaches Chandrasekhar mass limit, we will have type 1a supernova explosion, which, by the way, is believed to be one of the channels leading to type 1 supernova explosion. A higher mass white dwarf has a smaller radius, we know this, therefore it has a deeper gravitational potential well, therefore the accreted material is stronger compressed. This also reduces the total accreted mass before the nova explosion. The strength of nova explosion also is also amplified with a decrease of the white dwarf central temperature or white dwarf luminosity, because this slows down the heating up of the compressed accreted material. And this results, by the way, in the high accreted masses. The nova explosion is amplified with a decrease of the mass accretion rate, which reduces the gravithermal energy release rate, thus also leading to a higher accreted mass. Finally, the strength of nova explosion is amplified with an enrichment of the accreted envelope in carbon and oxygen that are most likely dredged up from the underlying white dwarf by convective boundary mixing, by Kelvin-Holzer stability, that is also needed to erase that helium buffer layer that I showed you before from the surface of a newborn white dwarf. You can have a look at this movie, okay, which simulates this boundary mixing event caused by Kelvin-Holzer stability, which actually adds carbon and oxygen from the underlying white dwarf to the hydrogen-rich envelope. I can go to this movie right now. Okay. So this is a movie from 3D simulations, three-dimensional hydrodynamic simulations of nova explosion. Okay, so this boundary is this line is the boundary between hydrogen-rich accreted envelope and underlying carbon-oxygen wide dwarf, and you can see these plumes. They penetrate into the carbon-oxygen wide dwarf, and they dredge up. They mix carbon-oxygen-rich material into the hydrogen-rich envelope, which facilitates nova explosion. Without this mixing, there would be no observed nova explosions. And there is a link to the paper, and you can have a look at this paper if you want, and this movie later. Okay, so let me just. Just a second. Okay, so I'm here. Okay, so now I have 15 minutes left. I will finish discussing this nova slides next time. Now I'm going to switch to show you how you can start running some simple simulations of nova explosions. Okay, because these slides are not relevant for these simulations. I will show them. I will show you them later. Okay, so therefore. Now let me switch to this screen, okay. So to start running simple nova nuclear synthesis, not explosion, nova nuclear synthesis simulations, this is post-processing nuclear synthesis simulations. In order to simulate nova explosion, we need to use either MESA stellar evolution code, and I will explain you how to do this later, probably next time, okay. But you can start doing simple nova post-processing nuclear simulations. For this, you should go to astrohub.uvik.ca, and if you downloaded this CaNPAN tools, the main directory has a README file, okay. And it tells you that for beginners, and let me call you yet beginners, for beginners, you should go to this TINA server. So you go to astrohub.uvik.ca and you choose this orange square, which is called TINA, for training in nuclear astrophysics, New Grid 1 Zone Network for Teaching, okay? So you click it. And then you spawn, you click this orange bar. This is also explained in the README file. Okay, you click the spawn orange bar, you wait. Okay, now you're here. The first thing to do, you open this README file here on the left. On the left margin, you open a README file. You don't just click it, left click. You click right button like this, right, and you ask open this file with Markdown preview. This one, okay. Then you just read these instructions. I'm not going to read them right now. I'm just give you a link so that you will start to explore this yourself. Because everything should work. If something doesn't work, please report to me immediately via CaNPAN Mattermost channel or via email. So you read these instructions, okay? And I'm going quickly through them. These instructions tell you that the next step you will have to do, you will have to go here on the left margin to Network School Directory. So you just double click it. You are in Network School Directory. And these instructions tell you, open this notebook, make new iProcess. Don't be confused that it says make new iProcess. It doesn't matter. You will also be able to run Nova simulations. Just click this make, double click, and you have this notebook open, make new user directory for iProcess calculations. Okay. The most important thing you will have to do here, you will have to provide here the name of your directory. It's up to you. Choose any name that distinguishes you from other researchers. For instance, here I click DPA. This is my initials, okay? And then I execute this cell, you know, how to execute cells in Python, Shift Enter, right? I execute this shell, and it will make a directory with this name on this server. Then it asks, checks if the directory name I picked is already exists. No, it doesn't exist. Okay. Next cell is important. It will clone computational tools into directory under your name, and this name, your name, okay, that you have chosen. Okay, cloning into DPA. As you can see, it's cloning into DPA. Now it's done. So next step, also important, it will add some data files that are necessary to run simulations. Therefore, just execute them. Step 5, just to check that everything was done correctly, you just run the next cell, and its text says it should produce something like this. Okay, so I'm going to execute this, and then just wait. It should produce something like this. Just check that it works. Yeah, you see, it produces something like this. Okay. You can wait, but you don't have to wait. You don't have to wait. Everything seems to be working. So therefore, I'm going to abandon this notebook. Now I go to the left margin, and you can see there is a new directory with the name I have chosen, DPA. This is my initials. There will be here a directory with your name, like Alex or whatever. It's up to you to choose the name. So now I go to this directory by double clicking it, DPA, okay? And you can see there are two subdirectories here, iProcess and Nova. So far, this time, we are going to study nuclear synthesis in Novi. So therefore, double click Novi, okay? But this first notebook at the very beginning here, it also explains that after you have finished with the first notebook, you will have to go to the corresponding nuclear synthesis directory. It says iProcess, but you will go to Nova, and in this directory, Nova directory, you will have to run these three notebooks. Model runner notebooks. Obviously, it will run model simulations. Result explorer notebook, it will analyze results, and rate changer notebooks, which will allow you to change some nuclear reaction rates and rerun your simulations to compare how the change of reaction rates changes nuclear synthesis yields, right? So therefore, in Nova directory, you also will find these three notebooks. So therefore, next step, let me just start these three notebooks in Nova directory under my name. You will have a copy of your own Nova directory under your name. So let me start model runner here, double click, results explorer, and rate changer, okay? Okay, so now I go first, I start with model runner, okay? You will see here, you will read instructions, of course. I'm not going to do this right now. It's up to you to investigate these notebooks. Step 1, you can choose from this table the one zone post-processing Nova nuclear synthesis simulations that you want. For instance, let me choose case number 3, which corresponds to this Nova model, and it shows that this Nova will have maximum temperature 436 million Kelvin. This is the highest temperature I have in this models. Okay, let me use this highest temperature. Case number 3. Okay, so I have to choose case here, as instructions tell you. I choose case number 3 here. Then I just run this. if everything is okay, the output should look like this. Okay. It actually provides here the time step, then the time, then the density and temperature. Not density, something else. It doesn't matter. Okay, now it's finished. Okay. Now this notebook, model runner notebooks, just suggests that you check that you have all files here. Okay, this is what the new files that were generated right now. Okay, so now it says this important step: create a new directory, new folder with the results. Okay, make a reasonable name for the directory. Because I run case 3, I'm going to make directory with name case_3, right? Save results in the new directory case_3. Okay. Now, again, let's check. Oops. Case number 3. Does it cannot accept? Why didn't it have? Okay. Okay, now it works. To try to execute the cell again, if by some reason it didn't. Yeah, so now everything is okay. Okay, so now that was a model runner notebook, which just allows you to run model and store results in a directory. Now let's go to Result Explorer notebook, okay, which will make some plot. So let me just execute it. You will read these instructions later. Okay. Okay, load data. Case. Check that you use right names for directories. Case 3, right? This is what my new name here. It reads the data. Okay, now it can make plots like this. Okay. Oh, what? Ah, there is no such. Yeah. There is a parameter here, the number of the cycle of time step to plot. Here I have only 386 cycles, but here I have 1,386. Okay. Okay, this is just isotopic chart of nuclides produced in NOVA. The color shows the decimal logarithm of mass fraction. You can see at this high temperature, the NOVA nucleosynthesis reaches calcium here. We can get quite high calcium abundances. Okay, now let's go further. Yeah, we can read that trajectory that was used to do this one-zone calculations. Okay, it just reads it, and we make a plot. So this is the plot of temperature and density trajectories, a trajectory that was used to run the simulations. You can see as a function of time in minutes, temperature is brown. Temperature has reached almost 450 million, and the black dashed is the density here. Okay. Now, a useful plot can be made with the next cell that will make a reaction rate flux plot. But for this plot, if I execute it right now, it will report an error. It says there is no this flux file. This is because I run my NOVA simulations without outputting fluxes. When I output fluxes, reaction rate fluxes actually, then it takes a longer time to run and larger volume of data. But I can do this. If you want to make the plot of reaction rate fluxes, you should rerun your simulation. So therefore, on the left panel, you go to NOVA. And in this case, you have to go to ppn frame. You open this file here. And you have to use iPlot flux option not equal 0, but instead equal 1. Because 1 will print fluxes. And then you have to save this file. Okay, save file. Okay, and now I have to rerun the simulations, and I will probably have to delete my previous simulation. For this, I have to open terminal. Go. Sorry, network. Nova. Everything is here. You can see case 3. I remove it. Case 3. Sorry. Okay. Now I go back to model runner, and I just rerun it. So I rerun my case 3 with reaction rate fluxes in the output. Now you can see on the left, there are flux files produced, and simulations now go a little bit slower. So it's up to you. If you need fluxes in the output or not, it's up to you to decide. Again, if you will have any questions during executions analysis, please ask me questions over Mattermost channel or via email. Okay. You see now it goes slower. We need to reach 386 steps because there is here on the left, you can see fluxes. These are pretty big files with fluxes. It takes a long time to output these big files. They can occupy up to 1 gigabyte actually. So we are almost done. Let me just finish. I have a couple of minutes more left. I want to show you a plot with fluxes because it's a useful plot. For this, I have to finish this run. We are in the middle. We need 386. Right?
Pavel, I just got a quick question.
Yeah. Mm-hmm.
So you're playing with MESA data right now. Is that right? Or
now in these are one zone simulations, which means
okay.
We simulate nuclear synthesis at one zone, but temperature and density change with time according to the prescribed trajectory, right?
Okay.
And
right.
This trajectory is taken from MESA-NOVA simulations from the bottom of the hydrogen-rich envelope where temperature has always maximum value, right?
Right.
But I do have a NOVA package which allows you to run NOVA MESA simulations and extract trajectory from there. But this is more complicated, and we will discuss this maybe next time. Okay.
Okay.
This is a second package for advanced users, but it's probably a good idea for you to start with the simple case because it's very easier to run. Okay. Yeah. And also, in principle, if you are interested, for instance, in studying uncertainty of reaction rates, you can run one zone simulations as a first step, right? As a first step. When you find in this one zone simulations which reactions are suspicious, they may have strong effect on nuclear synthesis. Then you can run multi-zone simulations with MESA and multi-zone post-processing, right? Usually it's a good idea to use this two-step approach, right? One zone simulations followed by multi-zone, right? Yeah, because one zone are faster, much faster. You can run Monte Carlo simulations with one zone model. It takes maybe 10 hours on a laptop, on non-Astro Hub server. Multi-zone simulations, Monte Carlo simulations, multi-zone will require a supercomputer, and they can run a week. I had such experience. So therefore, okay, now probably they are finished. Let me just store the results. Case 3 again. Case 3. Okay. Let's check that. Okay. Now I go to Result Explorer, and I am here. I have to run. Yeah. This is again probably from here. Let me read. Okay. This one. Okay, this is the chat. Okay, so now this plot of this is trajectory. Okay, yeah. So one zone simulations use this trajectory. So this is how temperature density change with time. Okay, and this is taken from real Mesa Nova simulations, of course, right? And we can do this later, not right now. And now we can make a plot of nuclear reaction rate fluxes here, because we have generated fluxes. Otherwise, it reports that there is no file, the right file for flux. Yeah, you can see this is a very instructive plot as well, because it shows you actually which reactions are important, right? Which reactions have a brighter color and a thicker arrow, okay? This is a very important thing, okay? So there are more plots here. Okay, just a second. This is decayed elemental abundances for this Nova case, and also non-decayed. And also undecayed Nova abundance. Okay, so I'm just encourage you to study these tools, okay? And I didn't mention yet, but there is the third notebook, rate changer. You can try to study it yourself, okay? It allows you actually to change some reaction rates, okay? And rerun your simulations and make a comparison. You can put new results with change reaction rates in a directory with different name, and then you can make a comparison plot, okay? I'm going to stop here. I think I've explained to you quite a lot of today. So do you have any questions? I'm going to stop sharing my screen. Do you have any questions? So let me just summarize. By the next Monday, I will finish Nova slides. Okay, I will start presenting for you this advanced package. At least I will show you what it can do, right? But it's a little bit more complicated, so you will need my assistance if you decide to run this package. And by the next time, please try to run this Nova cases, right? Go to UVic astrohub.uvic.ca and click orange square Tina. Okay. If you have any questions, ask me via Matrimo's channel.
So by advanced package, do you mean Wendy? Is that the?
Yeah, advanced package can be run on NuGrid Wendy. And for this, you need to become a NuGrid member. This is not a big deal. I just have to say to apply. And by the way, Alex has already. I mean, I didn't hear from Alex back, but I added him. So Alex got it.
Yeah, it worked. Yeah, sorry.
Yeah, oh, sorry. Alex.
Yeah, I was added.
Yeah. Okay, so if there are no more questions, I'm going to stop video recording and we are going to say goodbye, right? Okay.